Let's continue our production equilibrium with a second example. Now you are told to assume that a firm produces 90 units of output using labor and capital, and the firm's technological possibilities can be represented by this production function. Now if the price of labor is 1 rand per hour and the price of capital is 2 rand per unit of capital, the question asks what is the cost minimizing way of producing 400 units of output. So here you have your price per unit of capital, so that is your rental rate, and you have your wage rate as 1 rand per hour. So therefore you can derive your ISO cost line. And your ISO cost line is given by your wage rate times L plus your rental rate of capital times K, and that is equal to your cost. Now we don't have C. You can see none of that information pertains to your total input cost, but we do have our wage rate and we have our rental rate. So there's your ISO cost line, and you can rearrange it such that it is in the form of a straight line equation. K is the subject of the formula. So now you can very clearly see that your slope, which is negative and downward sloping, the function, your slope is given by the ratio of your wage rate over your rental rate of capital. So it is minus a half. This would give your vertical intercept of your ISO cost line. However, we don't know what C is just yet. So to recap, what is the slope of your ISO cost line? Your slope, you could rearrange your ISO cost line to view the slope, or you could see that your slope is given by the negative ratio of your input prices, W over R, the wage rate over the rental rate of capital, so minus 1 over 2 or minus a half. Right? Either way is acceptable for you to rearrange that ISO cost line to determine the slope or for you to reflect it. So next we can derive our marginal product of labor and marginal product of capital. Now in order to obtain this, we need to get our partial derivatives. Remember, this sign represents your partial derivative of your function, your output function, with respect to labor, and we treat it capital constant, and that will give us our marginal product of labor. And to get your marginal product of capital, you need to get the partial derivative of your output function with respect to capital, treating labor constant. So we need our partial derivatives. So let's go back to the function just to see the original function. The original function, output Q, is equal to 10L to the power of a half times K to the power of a half. So if I get my partial derivative of this function, so my partial of my output function with respect to labor, treating capital constant, so I'm just going to differentiate here. We have L. So I have 0.5, and I'm going to bring it down and multiply it by this coefficient of 10, and that's going to give me 5L raised to the power of minus a half. So I can put the L to the minus a half in the denominator, but I still have K to the power of a half because it's multiplied by, so it can't fall away. So therefore you're going to end up having, for your marginal product of labor, the partial derivative is going to be 5K to the half. K was still there, but L to the half was L to the minus a half. So therefore you can write it as L to the half. You can place it in the denominator. Now to get your marginal product of capital, let's reflect on the original function. So to differentiate, to get your partial derivative of this function, but with respect to K, K is raised to the power of 0.5. So you're going to bring that 0.5 down and multiply it by the coefficient in front of K, which is just 1. So you just have 0.5. K to the power of 0.5 minus 1. That becomes K to the power of minus 0.5. So therefore, you can put that in the denominator. So K to the minus 0.5 in the denominator would just be K to the power of 0.5. But remember, you still had 0.5 over here. So 0.5 times 10 is going to be 5L to the power of 0.5, and that would be in the numerator. So therefore, you have 5L to the power of 0.5, and in the denominator, you have K to the power of 0.5. Now you know that your marginal rate of technical substitution would be given by the ratio of your marginal product of labor divided by your marginal product of capital. Just bear that in mind. So now the question goes on to ask, calculate the amount of labor and the number of machines that are used to produce. Now this is not 40 units. Remember, it was meant to be 400 units of output in the cheapest possible way, given the above factor prices. So to determine your production equilibrium, or to determine the cost minimizing way of producing that 400 units of output, in order to do that, we need to determine that point of tangency where your ISO quant touches your ISO cost line at a point, and at that point, if you think about it graphically, the slopes of those two curves are going to be equal. Now, your slope of your ISO cost line, you saw was the ratio of your input prices, W over R, and the slope of your ISO quant line is the marginal rate of technical substitution, and that is given by the ratio of your marginal product of labor divided by your marginal product of capital. Right? And we know both those slopes are downward sloping, so they would be negative. So on the left hand side here, you can see we have your marginal product of labor divided by your marginal product of capital. This represents your marginal rate of technical substitution, the slope of that isoquant. And on the right hand side, we have our ratio of our wage rate over our rental rate, and that was minus a half. Now, just to solve this, to make it easier, we could change this to multiplied, and then this could be switched around or inverted. So now you have k to the half. Although the step is not shown, you would have k to the half in the numerator and 5l to the half in the denominator. Then I can just follow the rules of exponents, and I can say, because I'm multiplying, I can add my exponents. So in the numerators, I have 5k to the half plus k to the half. So therefore, the halves add up to 1. So I just have 5k. And in the denominator, I have l to the half, and it's multiplied by 5l to the half. So I just add the exponents. So I have 5l. So therefore, the 5s would cancel. The coefficients of k and l, which is both 5, that would cancel, and you'd be left with k over l. And you add a half on the right hand side, and of course the negatives can be cancelled out by multiplying both sides by minus 1. So therefore you could have k over l is equal to a half, and it can be written as l is equal to 2k, or you could say k is equal to a half l. From microeconomics ECO235, you know that this would be that optimal mix or bundle, right? So where do we go from here? So now you're going to take L is equal to 2k, and the reason why I took that, it is easy to work with that as opposed to saying k is equal to a half L. Just try to steer away from fractions if you can. So you have L is equal to 2k, but you also know that output, you were told, is equal to 400. So therefore, you can substitute these bits of information into the production function. So, and how do I know that? Because I was given Q, I was not given C. So therefore, I take that 400, Q is equal to 400, and I'm going to substitute it into my production functions. This was the production function. And then you also had L was equal to 2K. So remember, this was L in the original production function. I'm going to substitute 2K into it. So now you need to be careful with your math, your simplification. So remember, if something is raised to a power and it's in brackets, both the 2 needs to be taken to the power of a half, and the k must be raised to the power of a half. So therefore, on the right hand side, this just expands the steps quickly. we have 400 on the left hand side, and then on the right hand side you have 10. But now 2 is also raised to the power half, and k is raised to the power half, times k to the power of a half. I hope you understand that from the rules of exponents, which you were meant to revise as self-study in week 1, right? You raise both 2 and the k to the power of a half. So therefore, 2 to the power half can be written as the square root of 2. But here we have k to the half and k to the half. I can just add those exponents, and that's going to give me k. So now, from this step, we are able to go over here. We've rearranged this so that we have k as the subject of the formula, right? So you can see we had 400 is equal to 10 times 2 to the power of a half. So I can write that as the square root of 2 times k. So if I want k by itself, I'm going to have to divide the 400 by the 10 times the square root of 2, right? And that is the step. So now you can punch that into your calculator, and you're going to get k is equal to 28.2843. I would try to steer away from rounding off while doing a problem, and only round off to the end, and also read the instructions about how to round off. So now you have k, and now because you have k, you can now substitute it in over there to determine L. So L is going to be equal to 2 times what you have for K. So L is equal to 56.5685. So you have K and L, and now you can substitute that into your cost function, your ISO cost line, which was this function over here, because we have L and we have K, but what we don't have is our total input cost. So C is thus equal to 113.1371. Now there are 4 more practice problems. The first 2 practice problems are fully worked out. So work through it in your own time. Be very careful with how you deal with the exponents. You should be able to work through it. I don't want you to make mistakes with the math, but you understand what you are doing. So just be meticulous when you solve. So those are 2 worked out examples. And then the 4th practice question, right? And then there are 2 homework exercises, and these ones are easier because they don't deal with exponents, but don't expect easy questions, right? But you are given the answers, not the full calculation in this case. So please work through this to see that you do arrive at these answers. So I will be continuing with the Lagrangian multiplier in the final part video for this week. And for the Lagrangian multiplier, now we're going to be applying it to production as well. So previously you had dealt with the Lagrangian multiplier and you dealt with consumption. Now we're going to be applying it to production. And the prescribed work, it comes from chapter 8.4 of your prescribed textbook. And that is the reading that you need to do before we proceed with the next section.